It's most likely the case that starting with the conditions on Earth more than 4 billion years ago, starting that is with the proverbial primordial soup, amino acids can spontaneously arise. These amino acids result from the mixture of chemicals in the ancient Earth's atmosphere and oceans, along with the important energy ingredients of lightning and solar radiation. Amino acids are an important part of life's story because they're the basic building blocks of life, the pieces that make up protein peptides. In 1996, David Lee showed that a peptide made up of 32 amino acids in a chain exhibited crude self-replication abilities. For many, this is the surest sign of life. Finally, in a lab environment, someone had demonstrated life taking off. However, the major missing piece of the puzzle was how nature could have come up with that sort of peptide on its own. There are 20 different amino acids that make up our form of life on Earth. And there are 10 to the 41st power different ways to put together the 20 types of amino acids into a chain of 32. This is a staggeringly huge number. Most of the combinations do not lead to life. In fact, only one that we know of so far surely leads to some sort of crude self-replication. The problem, and it's an historical one as much as a chemical one, is that there doesn't seem to have been enough time for so many different combinations to have been tried in the history of the Earth. If life began this way, then how did the one right chain get created so quickly? Random chance would seem to rule it out. The second law of thermodynamics would seem to rule it out. And yet, here we are. The second law of thermodynamics is perhaps the most important rule about energy. It basically says that in all energy exchanges, if no energy enters or leaves the system, the potential energy of the state will always be less than that of the initial state. This is known as a measure of entropy, disorder in a system. In order to keep things organized, you have to pump energy into a system. Otherwise, everything tends toward disorder. When cream is dropped into a cup of coffee, the cream starts to mix and swirl with the coffee. At first, it's all bunched up and separate, but soon it's all chaotic and disordered. If you leave the coffee cup alone, the cream and the coffee will only move to greater and greater disorder, a chaotic mixture of the two. That is to say, you could wait and wait, and the cream will never spontaneously all decide to congregate on one side of the coffee cup. That would be order. For free. That just can't happen. The same thing happens with air molecules in your house. Hot air mixes with cold air, and the room temperature becomes an homogeneous mixture. Your refrigerator creates a little space in the room where there is order rather than disorder. For a few cubic feet, everything in the refrigerator is much colder than the surrounding area. This is a pattern, order, a lack of chaos. But it cannot just spontaneously happen. The only way to make it happen is to pump energy into that system. You need energy to power the refrigerator and make it possible to have a temperature differential in the kitchen. And indeed, even with this outside power, entropy still sends you a bill. The heat coming off the back of the refrigerator's coils and other operating parts increases the kinetic energy of the air molecules in the room, and thus their state of disorder. Chaos always wins. Entropy cannot be defeated. Order cannot be had for free. This is the problem with a peptide that can self-replicate spontaneously appearing on the scene. Such a peptide would contain a high degree of information and thus order within it. Its structure would not be chaotic, but precisely tuned in order to accomplish these lifelike tasks. Imagining such a peptide spontaneously forming thus seems to violate the second law of thermodynamics. It seems to be order out of chaos, order for free. This, then, is when the magic really needs to happen. There are some things in nature that are quite complex, but that do arise out of nothing. They seem, that is, in violation of the second law. A mass of air particles in the sky tend toward homogeneous mixing, just like air particles in the room. This is the highest entropy state for the air particles, their highest state of disorder. And yet, there are phenomena that arise from time to time in the atmosphere that are highly organized. Hurricanes and tornadoes, for instance. These organized collections of air particles might seem an impossibility. How can such isolated pockets of complex order arise out of nothing? The answer is had when we look at the bigger picture, when we look beyond the individual phenomena and ask instead, what does that phenomenon do to the rest of the community? And with a tornado, the answer is clear. A tornado itself is a very highly organized thing, but the main thing that it does is cause high-pressure systems and low-pressure systems to mix and increase their entropy. In fact, a tornado is often the most efficient means of doing this mixing. Thus, it should be no surprise that nature turns to a whirlpool to get this job done. In the words of Dorian Sagan, Carl Sagan's son, and a bright intellect in his own right, nature abhors a gradient. This is one way of stating the second law of thermodynamics. A gradient of any kind has a high degree of order, high complexity. There's a lot of something on one end, a little of that thing on the other. For a pressure gradient, one area will have high pressure, the other will have low pressure. This gradient has lots of organization. But entropy, wanting to do its work, desires chaos over organization. The state toward which the system will thus move is one in which the pressure will be the same across the board. No pockets of high and low, no discernible differences in pressure anywhere in the sky. When conditions are right, the quickest, most efficient way to move from the gradient to the flat line, from organization to chaos, is through the creation of a tornado. Viewed singly, a tornado thus seems an energetic, complex anomaly, an organized individual thing that just shouldn't arise. But when viewed as part of the larger system, it makes sense to say that this little, brief pocket of order should indeed arise. For its ultimate role is to serve entropy, to create disorder, to destroy that gradient, to live for a little while, serve the purpose of the second law of thermodynamics, and then disappear into thin air. And so are we tornadoes. Life is highly organized. It seems impossible. Why should individual living things, highly and complex in order, ever develop out of chaos? Because life has a purpose. Thermodynamically speaking, life's purpose is to destroy gradients. Most importantly, the energy gradient created by the hot, burning sun and the cold space that surrounds it. All of life on Earth is based on taking the energy from the sun and dissipating it. Plants and animals are tied to the sun's energy for their existence. And what we're learning now is that when living things take in that energy and disperse it through various means into their environment, they increase local disorder, raise the general entropy, and help to even out the huge electromagnetic energy gradient that exists between the high-powered sun and the frigid space of our solar system.
Gigantic nuclear furnace where hydrogen is built into helium at a temperature of millions of degrees.